Now it's recording.
Okay, so I restart. So thank you very much again for this introduction. I'm very happy and honored to have the chance of giving this talk, and I would have loved to be there with you, which means that I will be double loving meeting you in the future sometime. So, yeah, so I will be talking about some existence resulting morphoelasticity. This is very recent work, which I did in collaboration with Elisa Davoli, she's in the audience, and working at the Technical University of Vienna, and Katerina Nick, she's a postdoc in my group in Vienna. So let me jump into the business by discussing a little bit what is morphoelasticity. So I'll leave you a couple of seconds to admire this piece of art, which I put on the left, my carrot. And so the carrot will be leading out my talk. So here it is. So morphoelasticity is the combination of these two effects. So elasticity of some solid, some continuum solid, combined with its growth. Its first application is to biological systems, and this is the reason why I put here a carrot. Usually biological systems change shape with time. They even grow or maybe shrink or maybe reorganize by means of a number of phenomena which happen at different scales, and of course, very rich and interesting, but way beyond my expertise. So I will just mention some of these. So it's listed here. So cell division, this makes living beings bigger and bigger. Morphogenesis, which means that some cells, a long time, they change shape and function. This is also a little bit the content of differentiation. With proliferation, we mean a kind of an uncontrolled mesoscale cell division, and this you can connect with some of the pathologies which afflict mankind, like cancer. And remodeling, this is also very important. The remodeling is the effect of living systems to change their internal structure or maybe their density without changing shape. For instance, a bone, which is subject to some load, will usually get thicker and thicker, denser and denser. So morphoelasticity, the change of shape and then elastic, it's also applicable to other systems which are not of biological nature. So for instance, accretion, you imagine, for instance, a snowball rolling down a hill. This will change shape by adding material and material on the surface. Another way of growing at the surface is epitaxial growth. You may consider growing a crystal by just depositing layer on layer of this crystal. That's also a growth process. Swelling is also a very common process. So gels are usually changing volumes by many factors if you put them into a solvent. And I just want to mention here the additive manufacturing. So if you are 3D printing something, usually you're going to be depositing layers on layers of material, and at the end you will have a big solid. Okay. So none of the details of this modelization are of my interest today. I just want to discuss with you some basic principle and describe to you some existence results. So the first step toward the description of this is for me to discuss the possibility of describing morphoelasticity as a composition of maps. So here on the left, indicated by omega, I think you can see my pointer, right? So indicated by omega, you have what I would like to call my initial shape, so my baby carrot. And then I imagine that over time, the baby carrot has changed and has gained its actual shape. So this would be the grown shape, the G of omega. And I imagine at this point that this transformation from the initial shape to this grown actual shape is done through this mapping G. You can imagine this to be very smooth and also injective. And then it's this grown shape that you would like to elastically probe. You would like to apply to this grown carrot your loads and see how they deform. So by applying loads to this grown shape, you get the actual shape, which is the final one on the right. This is the deformed carrot. So now I'm imagining that the final deformation of the curve, this y here, is actually the composition of two other deformations. The first one, little g, is the one that describes the growth. And the second one, y of e, is the elastic deformation on the grown shape. Okay, so we see the full deformation of the curve as the composition of two maps, growth and then elastic deformation. Okay, so if we see this, then let's do a step. And let's assume that the response of my curve is hyperelastic, which means that I can associate to the gradient of my elastic deformation and energy. And I would like to look to those possible elastic deformations which are kind of minimizing this energy. So this is what happens in this pink box here on the left. So I'm minimizing on all the possible elastic deformation ye, the one that this integral. This is the integral of the elastic energy density W. And this elastic energy density is integrated on the grown shape, G of omega. So again, the grown shape is down here, and the variable in the grown shape is this little x. Okay. But now I told you the G, which is this map describing the growth, is the best map possible. It's injective, and you can think of changing variables using this map G. So this means pulling the whole problem back to the initial shape, which could have the advantage that the initial shape is initial and it's fixed in comparison with the grown shape, which changes with time. So the variable in the initial shape, I'll call it big X, and this is just a change of variables in the gradients. So the gradient of the y, it's a composition map. It's just the product of the gradients. So I'll take the integral, which is inside the pink box, and I just change the variables. And what I get is in the pink box at the bottom. You see, now you have an integral, which is a function of y and small g. And this integral is all defined on the initial shape. And it features here the determinant of the gradient of small g because you change variables, and this is the term that you need to have here. So in particular, you see here, I put no absolute value. And the reason for this is that I imagine that this gradient will not change orientations. So it's really what you can imagine from my picture. Okay, so let me go one step further. So let me list some critical issues with this approach. So again, the energy that I want to minimize is here at the bottom. So it's the integral of the initial shape of this product of gradients times the determinant. And so with this way of looking at the problem, we get some troubles. And I've listed some here. So first of all, this issue of the initial shape. So the many of you in continuum mechanics know that the reference shape for the deformation is arbitrary, and the change of this should be possible inside your model. And this is also true here. So you are deforming from an initial shape, but it's even worse here because the initial shape is the starting of an evolution. So in a sense, you shouldn't be so free in changing it. Plus this evolution, in the example that we just discussed, may change kind of at other scales. So when you're talking cells, and they become collections of cells and then solids progressively. So the initial shape business is, to me, a little bit problematic. A second issue that I want to mention you is mass. So by growing, mass is, of course, growing, which is something that at the moment is not respected in this functional that we see. Look at this functional, this is just a change of variables. We got it by changing the variable, so we can imagine that the initial density, so the density of the initial shape, is just changed by this little function little g, and as volumes change. So in a sense, the initial shape and the grown shape, they have the same mass, which is usually not the case. A third issue is the possibility of having stress-free states. So now the way the energy is defined, it's kind of suggests that the last elastic step is starting from a stress-free state, which is a ground shape. This is very hardly the case. So ground shapes are usually in equilibrium, but they feature also a variety of internal stresses which are blocked inside the shape itself. You can see this by actually making a kind of an experiment with a carrot. So you take a carrot, maybe an old one, and you cut it open in the middle, and it will buckle a little bit, meaning that it releases some internal stresses. I also have an example here. In my office, I hope you can see this. I hope you can see this piece of wood. Maybe you cannot, but you have to look at me in the little gallery of faces. And of course, when I got it, it was not cracked. And it did crack because it lost some water over time, which made the volume kind of smaller, and this volume was not attainable anymore. So this stress was released by this crack. Okay. And then my first issue is the one of incompatibility. So in fact, this nice transformation little g doesn't exist. And in most cases, you cannot really assume that this exists. So we should be able to live without this. Okay. So for point 1, 2, and 3, I would have solutions, which will not be included in this talk, however. But for point 4, there is no solution. So I really have to drop this idea of having a small g as a descriptor of my growth, and I have to be a little bit more general. It's exactly the step that you would do for inelasticity or maybe finite plasticity, and here it is. You should forget about maps and resort in talking about transformations of tangent spaces. So we forget about the fact that we have a map small g, and forget about the fact that we have a map y of E, that's the elastic deformation. And we replace their gradients by just these tensors. So the tensor big G, this takes the position of gradient of y, which might not exist. And the tensor big F of E, this takes the place of the gradient of small y of E. So the composition that we had, it's still good. So we still can write the gradient of y as the product of 2 other tensors. Just these tensors are not gradient anymore. And this relates to the fact that, again, maybe this grown configuration in the middle is not well defined. And we are just lucky because we can go on with the theory without really knowing what configuration we have here in the middle. We just need to know how the tangent planes transform one to each other. And this is the drawing that you see here. So the blue tangent planes. Okay, so let's go on with this, and let's step to the second part of the model, which is the growth dynamics. So here, a little bit of magic comes in. So if you go and look to the books, you will find this kind of bodies over and over. So this is a phenomenological model. And it's the equation for my tensor G, which I will call growth tensor from here on. It's a time-dependent quantity, so you see the dot. And it's just assumed to have this form. So the evolution of G is modulated by this other tensor M. The tensor M is the growth rate because it multiplies G again. And it can depend on many different quantities. I am listing some here. So it may depend on time. So you may be growing tomorrow faster than today. It may depend on big X. This is the position on the initial shape. Maybe some part of your initial shape are growing faster than others. Of course, it may depend on G as well, just to make it more nonlinear. It may depend on Y. This is the actual position of your body in 3-dimensional space. So you can imagine your carrot is still in the soil, so it's growing, or maybe it's already in the basket, so it will not grow anymore. Okay, so the position of the object. It can depend on the strain. And it can also depend on the stress. So with this P, I indicate here the first Piola-Kirchhoff stress tensor. The fact that growth depends on stress is very common. It applies to human beings. So again, I do again the example of the bones. So if you visit the International Space Station, your bones are going to get lighter and lighter because gravity is microgravity. So less stress, and then there is a growth or a degrowth of your bones. But examples are everywhere about this, about the dependence of the stress of the growth rate. And it can depend on many other things. So here, for instance, I'm putting a mu. This could be a concentration of some nutrient, or maybe if you want to think about tumor, some chemotherapeutic drug. And then also some of the other dots, because this can be coupled with other multiphysical effects. So for this talk, I would just, for this talk and in our paper, we did a kind of a simplifying assumption. We just took some of these. So we dropped the non-homogeneity here in time and space, because this is, in a sense, easy to handle. We also dropped momentarily the dependence on the nutrient. And on the position, this is also easier to handle. We wanted to keep the dependence on the growth tensor and on the strain, because from a composition of these two, you also get, in a sense, also the stress. So we dropped the stress, but we kept these two. Okay. So here is our morphoelastic problem. It's the combination of quasi-static equilibrium with growth dynamics. So the quasi-static equilibrium is that for almost all times, my deformation has to minimize the energy given a specific growth tensor G. So G is given at time t. So the energy is given depending on G, and Y at time t is minimizing this energy. So here you see no loads. I just wanted to simplify everything, but of course loads can be included. For the growth dynamic, I have the ODE that I just wrote. Just for historical reasons, I'm taking the G inverse to the left-hand side. So G dot G inverse is equal to N, and it was the growth rate. So this has to be fulfilled in the sense of tensors everywhere, almost everywhere in space and time. So I won't be very technical in my talk, but let me just mention that I remind that W would be a polyconvex density, so that when I integrate it, it's going to be weakly lower semi-continuous. We assume it to be coercive with a nice coercivity exponent bigger than space dimension, and also some control of stresses with respect to the energy is assumed. So these are the, let's say, the easiest setting where you can have existence for polyconvex materials. My growth rate M is a function of these two tensors, and I assume this function to be smooth and bounded with its derivatives. So in particular, the state is a couple, is the pair of deformation and the gradient tensor, a growth tensor, I'm sorry. Both these quantities depend on time, and they take values in this space. So W1P for the deformation. The deformation is a vector, and I also indicate here with a little symbol the fact that I imagine my carrot to be fixed somewhere in space, not to make it flow away by rigid body motions. And the G, as you will see, is going to be a nice function, so bounded with bounded derivatives later on. So it's a function of every point in space with values in the tensors. Okay, so let me now, in the next slide, remove these assumptions, which I now consider as given and fixed for the whole talk, and go to some comments. So the first comment that I want to do is that this model is very likely in the class of creep models. In fact, it's an elasticity model, and the flow rule has this kind of linear behavior on this tensor G dot G minus 1. So it's not exactly a creep model because, say it again, this M here is just purely phenomenological. So it's not a variation of an energy. And in fact, you cannot really have an energy balance for this system. You cannot expect this. And this makes it a little bit of a trouble in one sense, because you're not allowed to have variational notions of solutions, and you need to be finding another way to estimate your quantities along the evolution. Right. Okay. This is also the right point to point to this paper by Alex Milke, Riccardo Rossi, and Giuseppe Savare on viscoplasticity, which is kind of close in aims, and the dynamic is kind of similar. In that case, the M is the variation of an energy with respect to this variable G. So this is a little bit of a difference, which makes them, which makes available for them some variational formulation. And in this paper, there is an existence theory. This existence theory is using also the fact that there is another gradient of G into the energy, which we don't have. Okay, so again, in connection with plasticity, let me mention that so the shape of this energy is very common in plasticity. The only thing which is kind of a little bit different here is the occurrence of this determinant term. I've never seen it in plasticity really, and I guess that this is because usually plasticity is assumed to be isochoric, so is assumed to conserve volumes, and in this case the determinant is equal to 1. But I also checked into finite plasticity model where there is no isochoric assumption, and there as well, I never find this determinant of G, which is otherwise very, very common in morphoelastic papers. So let me talk about the separation of timescale maybe a little bit later, and let me talk again about this determinant business here. So of course, if you see the determinant showing up in the energy, then you will have trouble. So you have to find a way to bound the determinant from below. Otherwise, your energy will not be cursive the way you want it to be. Okay, so let's keep this in mind that at some point we will have to have a lower bound on the determinant almost everywhere in space and time. And now let me justify a little bit what I'm doing here with this quasi-static equilibrium problem by discussing this classical observation on the separation of timescales. So for morphoelastic problems, there are different and well-separated timescales. The fastest one is the one of mechanical equilibration. This is the, let's say, the timescale at which bodies reach the mechanical equilibrium, and it's all usually within, I don't know, a spectrum of hundreds of seconds. So you can think of banging your carrot on the desk and you hear a sound. This means that the equilibration happens into fractions of seconds. And then there is also a viscous scale, which is usually much longer, so it's maybe seconds already. There is a scale for your loading, the way you load your carrot, which can be even slower. And then there is a scale of growth. Growth usually happens in hours or days. It may happen in minutes if you really have bacteria which are really super active, but not carrots. So scales are so separated that I think a good way to look at this would be to have quasi-static equilibrium for the mechanical part and then an ODE for the growth dynamic. Okay, but this makes troubles. I know I have experts in my audience, and by looking to this problem, you see immediately there is something missing. The point is, you can control the time evolution of G because you have an equation with a G dot inside, but there is no way you control the time evolution of the Y. In fact, this minimization problem may have many solutions, and they may not depend smoothly on the G. So how do you do? So the only way we had to do this was by introducing a regularization, which you now see in red, very big, and it's there. So in the equation for the growth dynamics, we're not just taking the gradient of Y, which is not compact in time, but we are regularizing it. And we're regularizing it by a non-local operator in space and time. It's a regularization. And it might take the shape that you see here. It could be a double convolution where you convolve a time kernel with a space kernel, and where you apply everything to this gradient of y bar. The bar means that you extend it trivially outside of omega. Okay. So again, so to make it clear, so we are able to tame this problem just because we introduced a regularization at this point. Otherwise, we will have no chance in surviving the compactness, the lack of compactness of the problem. And but yes, since this is a regularization also in time, in fact, it's a kind of a way of introducing a time scale for the y as well. This is at the level of a viscous time scale. So again, it's something which is intermediate between the growth time scale and the mechanical time scale. Okay, so this big K is this regularization operator. It's linear. Okay, so let me show how we can show that this problem has a solution. So what we do, we time discretize it. So we chop time with possibly uniform time steps. You see it here, it's indicated by tau. And at each time step, we'll look at the problem that we had before, and we try to get the new values of the deformation y and of the growth tensor g. So the deformation y is just a minimizer, one of the minimizer, maybe many, of this energy given the growth rate, the growth tensor gi. This you can always solve. So if you give me a gi which has a determinant well separated from 0, I can find a solution to this because my density is coercive and polyconvex. And for the g, we define it explicitly starting from the old g. So gi is just a function of gi minus 1 and of the deformations up to time I minus 1. The way the deformations come in is through this operator k tau. You remember k is the regularization. This is a discrete in time convolution version of it. So it's an approximation of it. Explicit form you can imagine is just a sum instead of an integral, but we don't really need it. So I don't detail it. I'll give more detail on this. An interesting point is that we found practical to use this exponential scheme. So you see here, this is the exponential of this tensor. So I take the matrix M, I multiply by tau, and I apply the metric exponential. And with this one, I get the new GI. So this is very close to being an Euler scheme. And we can check it by just going to this first line and then computing the expansion of the exponential matrix. So if the argument is small, and it will be small because M is bounded and tau will go to 0, then the exponential is nothing but the identity plus tau M. And if you do the algebra there, you find that then to first order to have this exponential scheme is the same as having an explicit Euler scheme here on the right. So the way we like this scheme is that it's very practical when you have to compute determinants. So the determinant of GI is just the product of the determinant of this exponential matrix and GI minus 1 by the linear rule. And then the determinant of the exponential is the exponential of the trace. But since M is bounded, then the trace is bounded below. So if you put these things together, you see that passing from the determinant of G at some time step to the next one, the determinant could become a little bit smaller, but it's like it becomes smaller in a controlled way. So by iterating this argument, you have the determinant at each time step is bounded below by a number if the initial determinant was already bounded below. So this is the way we use to ensure that the determinant is always well separated from 0. So it has to start from an initial tensor, which is well separated from 0, whose determinant is well separated from 0, and then it can degenerate, but not that fast. And up to some final time, this will be separated from 0 again. Okay, so from this point on, I can assume that this determinant is well positive uniformly with respect to the time step of my partition tau. So this I will use in particular when it's time to find a priori estimates. So let me discuss first what happens for the growth tensor. So the growth tensor fulfills this linear equation where actually this coefficient m is nonlinear, but let's say that this, let's consider it this way. So you go for the infinity norm, you split norms, and you then you control the norm of the exponential matrix with the exponential of the norm of the matrix, and this you iterate over time steps to come to the initial step. So you see the infinity norm is bounded, infinity in space, and if you apply a gradient to this argument, it's going to be slightly longer, but you will get again a bound, a uniform bound in I. And you can even bound the gradient of the derivative in time with kind of the same techniques. Of course, to go for gradients and derivatives, we use the fact that the function m is differentiable and has nice derivatives. We said already that the determinant is bounded below. And with this lower bound, we can also bound the gradient of the deformation via a bound on the energies. So you see the gradient of the deformation is bounded by the product of what happens, what appears inside the energy with something that you already know bounded. And then you can squeeze in also the determinant if you like. So you see this is just bounded by the energy up to stuff which you already know it's bounded, all separated from zero. And the energy at each time is bounded by some reference energy, which could be the energy of making nothing, so the identical deformation. Okay. Okay, good. So my tensor G is bounded in space and time, discrete time. Its gradient and its time, discrete time derivative are also bounded in space and discrete time. And the y's are bounded in discrete time with values in this Sobolev space. So this is enough to start identification, so a passage to limit procedure, which goes along fairly classical lines, but for this point that I'm mentioning here. So the deformations are going to be completely converging in an infinity of W1P. This is the Sobolev bound which we just said. And the G's are going to be strongly converging uniformly in space and time, actually much more, but this is enough for this argument. So our point is now to check the minimality. Okay, so these convergences are, and the compactification property through this no-local operator K are enough to pass the limit into the growth dynamics. But what about the Y, so the deformation? The deformation is minimal for almost all T's, and the way you prove this, you pass to limit, to a lower limit on the energy up to some time integration. And at the very end, you squeeze the radius of this time integration to 0, so you can establish this minimality for all points which happen to be Lebesgue points of this scalar function that you see at the very bottom of the page. You can prove that this is an integrable function, and for all its Lebesgue points, which are almost everywhere in 0t, you check the minimality of y. Okay, so now based on this existence result, we are moving a little bit forward. And we're looking to a kind of slightly more complex problem where we also have a nutrient growing, driving this evolution. Okay, so this would be the nutrient-driven morphoelastic evolution. So the carrot is somewhere, and it's fed by this water, maybe, or this nutrient that you see there. So I give you this nutrient, this mu, this red mu, and the problem is exactly as before. So the Y is going to be almost everywhere minimizing the elastic energy, given G, and the G follows this ODE where you have an extra entrance here for this red mu. This is the concentration of the nutrient once again. So you see this problem, it's just a version of the previous one where this nonlinearity M is also depending on time and space in a sense. So you can reproduce the existence theory that you already saw, and find also in this case a solution, meaning a pair y and g solving this problem giving you. And you can think of using this to study an optimal control problem, which could be formulated this way. So you have a solution operator. So for all mu's inside some class of admissible nutrient distributions, your solution operator S is giving you a y and a g. So to be fair, this solution operator is giving you more because we don't have uniqueness. So this pairs y and g can be many. So the solution operator S is actually multi-valued. And then you can look at this minimization problem. So maybe you want to minimize this quantity J of Y, G, and mu, under the constraint that the Y and the G are solutions given the nutrient mu. So this is a general optimal control problem, which now we tackle just at the level of existence of optimal controls and optimal states. And the way you do it is at this abstract level always the same. So you assume to have a functional situation where the graph of this operator S is compact, and at the same time J is lower semi-continuous. So these two things together give you existence. And yeah, I know existence is just the first step, and it would be nice to have conditions, but in this case, these are a little bit out of reach because you didn't even know that that S is single valued, so it's going to be technical. We didn't do anything in this direction, but I would just want to mention an example of a possible functional J to be minimized. So here it is, it's a sum of three things. Now, for a second, just forget the happy example of the carrot and go to the sad example of the cancer. So now the first term is the determinant of G. It's kind of talking about the volume of the grown configuration, if there was one, at final time. So to minimize this would be to minimize the volume of the cancer at final time. Or you could say that another way to prescribe how big this structure would be is to minimize the difference, the distance of the deformation with respect to a target one. This is also a possibility, and this is given by the second term. The last term would be modeling the fact that maybe to influence this growth, or actually this shrink, you would need to give some drugs, and these drugs have counter effects. So you want to minimize the amount of drugs that you want to give. So here you also want to minimize the integral of mu. Okay, so for this kind of problems, we have an existence result. But then let's go to another and final evolution of the problem, which is the nutrient diffusion and morphoelasticity combined. You can also think of a concentration mu, which evolves in time, and whose dynamic is also influenced by the rest of the problem. So here mu is not given anymore, so mu is part of the problem. It's an extra variable to be solved for, and we assume that mu is diffusing. So when you see, you have a diffusion equation for mu, a linear one, and the evolution of mu is pushed by possibly source h, which we assume to be given. But it's also influenced by the body, and this influence is modulated by this maybe smooth function big H. So let's see. So what do we intend with this? So so the carrot is using the nutrient to grow, and in some places, as I said, maybe these nutrients are available and some others are not. So we can imagine this consumption depends on the position of the carrot. So all that we write here is referential. So we're describing this diffusion in the referential variables. And for the sake of definiteness, we decided for Dirichlet conditions. So this is the picture that you see here. So imagine the nutrient is water. So one side of the carrot is wet by water, and water then diffuses inside the carrot. By changing this mu, you change the way that the growth rate, so you change the growth rate, so you change the growth tensor, and then the growth tensor influences again the equilibrium, so you change the position, and everything is then completely coupled. So for this system as well, you can prove an existence result, again by time discretization.
Ulisse, would you mind taking question? I think Stephen Watson has a question. I think.
I'm sorry. Is it in the chat?
Yeah.
No.
Yeah. No, if I could quickly. So the growth, this mu depends on you're showing us the deformation and not the deformation gradient. Is there any?
Yeah. So this is I'm sorry. So we decided for this as a first.
No, that's fine.
As a first try on this, and of course, I think you could be sensible to have this age depending on many things, and maybe the stress, and maybe time, maybe.
I guess the motivation was that you regularized the tensor G with this convolution in grad Y, and I wondered if you basically had a similar structure in mu, you could drop the need for that in the middle equation. Okay, so.
Well, I'll take this question. Thank you very much. Sure. To point out something that I didn't say. You see, there is a K also here. So here again, I have the trouble that I need to be regularizing some. Again, there is no control in the Y dot. So somewhere has some compactness in time has to show up somewhere, and this is the point where I'm squeezing this compactness. If I'm really looking to Y and not grad of Y, I don't really need to be compactifying in space as well. But if I was using the same K as before, so a convolution in space and time, I could have here a gradient of Y as well. This would be from the analytical part, no trouble. I hope that this answers a little bit.
Yeah, thank you.
Good, thanks. Right, so, okay, so, of course, this is a kind of an initial thing, and many things maybe more interesting are to be done yet. And so, for instance, I can imagine that this diffusion actually happens in the actual configuration of the carrot, and not the referential one would be more interesting. And maybe in this context, other boundary conditions would be more relevant. And we just went for the first one, and again, we could solve because this problem has exactly the same parabolic problem as the other one. And so either you have compactness by controlling time derivatives, or you have compactness because of this regularization K terms. So again, there's a K here, and a K there could be even the same K. All right, so I think I am at my final slide, at my final time as well. So here are my conclusions. So we studied this finite strain quasi-stationary morphoelastic model. Again, we do not want to contribute to the discussion about this modeling, but just show that this kind of problems can be treated by classical analytical tools of continuum mechanics for inelastic problems. For instance, one can prove that a solution exists via passing to the limit into suitable time discretization. Here, the new thing, at least for me, was the use of this exponential scheme, which is otherwise pretty well known by engineers in finite plasticity. And of course, this basic result can be extended, and we wanted to look to some optimal control problem via the control by the nutrient or the chemotherapical. But this nutrient can also be completely coupled in a kind of a diffusion plus morphoelastic elastic system. So if you are interested in this, this is our reference in the archive. We have a version there, and the second version is coming. So please, if you consider downloading, maybe do it tomorrow when the new version will come, and some typos will be corrected. And with this, I think I'm ready to stop, and I thank you very much for your attention.